Assignment 3, 1.3 dilation and translation of given functions. So our essential question is, how do you transform a given function using dilations and translations? So remember, a dilation basically stretches or shrinks a graph, and translations shift a graph around. So we are going to be using the parent function f of x equals the square root of 1 minus x squared. This is basically a semicircle. So you can see this dotted line right here. That's the parent graph. Okay, that's y equals f of x, and our f of x is, again, the square root of 1 minus x squared, which is a semicircle with radius of 1. We're going to do some transformations on it, and we're going to start with dilations. So, and they did these in your book. They definitely go through and they talk about it a lot more than probably I'm going to, so you might want to read your book. But we'll start with dilations. There are two different types of dilations. There's a vertical dilation, which they also call, in this textbook, they're calling that an outside transformation. And the reason it's an outside transformation is because it's being multiplied to the function. So here, our vertical dilation, we're being dilated by a factor of 3. Okay? So all this is saying is that anytime the parent function is multiplied by a value k, so our parent function is f of x, and we're multiplying that function by k. So here, our parent function is the square root of 1 minus x squared, and we're multiplying that, our k here is 3. Okay, so this is important to know. You get a vertical stretch if k is greater than 1, which makes sense because, for example, here, my output originally in my parent function is 1. Well, I take that and I multiply it by 3. That's a number that's bigger than 1, so it stretches it up to 3. That gives you that vertical stretch. Okay, so you get a vertical stretch if k is greater than 1. You get a vertical shrink, though. Imagine if you took these outputs and you multiplied them by a fraction. Well, then they're going to shrink, right? So originally my output was 1. If I had multiplied it by a half instead of 3, then I would have shrunk. I would be down here, so that would be a vertical shrink. And the way that you get your outputs, you're going to take your y coordinate. So originally you have x, y. You're just going to multiply the y coordinate. So it becomes x, ky. So for example here, one of my points was 0, 1. That's in my parent function. And then I took that output, right? And so it should be, my output is getting multiplied by that dilation factor. So my new point is going to be 0, and 3 times 1, I can write it like that, which basically is 0, 3. So 3 is my k. It's getting multiplied to the parent function. Okay. So that's a vertical dilation. Now we also have things called horizontal dilation, so where we stretch it horizontally. Now a horizontal dilation is called an inside transformation in your textbook, and the reason for that, so look at what we've done here. We still have the same exact parent function, but we've multiplied the input by something. Actually, you could think of it as dividing the input by 5, or multiplying it by 1/5, because dividing by 5, multiplying by 1/5 is the exact same thing. Okay, so anytime the input of the parent function is multiplied by a value k, so that looks like this. Notice the k is not being multiplied to the function, it's being multiplied to the input of the function. Okay, so you're going to get a horizontal stretch. This is opposite of what was going on up here. You get a vertical stretch if k is a fraction in between 0 and 1. You get a horizontal shrink if k is greater than 1. So let's look at this one. Let's see, let me start here. So the way that you get your new coordinates is you now divide the x coordinate. Okay, so xy becomes x divided by k, y. So I'm going to take the point 1, 0. I'm just choosing easy points, like points that are really obvious that I can see. Okay, I'm going to take that, and now the x gets divided. So I'm going to take my 1, I'm going to divide it by k. Now k here happens to be 1/5. Okay, and then my x or my y stays the same. Okay, so what does that equal? Well, it's 1 divided by 1/5. Well, we don't divide fractions. Instead, you multiply by the reciprocal. So your output, or your new point, your new input is 5, and your output stays the same, 0. So this point dilated in the horizontal direction to this point. Okay, and the same thing would happen if I did that in the negative direction. Okay, so what happens when you put it all together? Well, when you put it all together, first of all, I should talk about preimage and image. So preimage is your original function. The image comes after the translation, or basically any transformation. Okay, so the image is after transformation. Some of them will just be a dilation. Some of them will be a translation and a dilation. It just depends. The preimage is before the transformation. So still sticking with the exact same graph, same parent function, but now we've combined. Well, you know what? I'm going to do one quick highlight here so that we can see that this was what we were talking about, 1/5. So now we've combined both the vertical dilation and the horizontal dilation. So we have the vertical happening, we have the horizontal happening, and so together we end up with, that vertical stretch, but also that horizontal stretch. Now again, if 3 had been like 1/2, then it would have shrunk smaller than the parent graph. There would not be this vertical dilation. There would be a vertical shrink. And if 1/5 had been a number, let's say, bigger than 1, then you would have had a vertical or a horizontal shrink. Okay? So let's just look at one more example, maybe in your, I think that the vertical dilation is super easy, but I want to just go back over that horizontal dilation. So here was another graph that you did in your exploration. And I'm just going to take this point right here. So this point was 2, 0. Is that right? 2, 0. Now, what I had in this graph was I was taking my input and I was multiplying it by 1/2. So that means in order for me to get my new point, I'm going to take that 2, 0. So let's see. I need some paper to write on. I'm going to take those points, and you pick the ones that are obvious, right? So this one's 2, 0. And I'm going to take, according to my notes, and this would just be something that you memorize, you're going to divide x coordinates. Okay, so anytime that you've got something being multiplied to your input, you're going to divide x coordinates. So I take my x coordinate, which now gets divided by that dilation factor, which is 1/2. So I get 2 divided by 1/2, 0. Well, 2 divided by 1/2 can't divide fractions multiplied by the reciprocal, so it becomes the point 40. And that's exactly what we have here. Let's see. 40 became that dilated point, or that new point after the dilation. Okay, and if you had a factor instead of 2, right, that would be a shrink, a horizontal shrink. So you divide 2, the original input, by 2, and you'd get 1. So you would see that, that point would now be here. I think that that's probably the newest thing for you. So I just wanted to go over that. So, in that question it says, how is that factor related to 1/2 and f of 1/2 x? Well, basically it means that you are horizontally dilating by a factor of 2, right? Because you would take any point and divide it by 1/2. Well, dividing by 1/2 is the same thing as multiplying by 2. So you're really dilating it horizontally by a factor of 2. So if you didn't get that in your exploration, now you have it. Okay, so that was the hard stuff. Now let's do the easy stuff, because we did this a lot last year. So transformations, shifting up, down, right, left. Okay, that's transformations. And the way that we looked at it last year was, I said, well, if you had a function, maybe it was f of x minus h plus k. Right? So your minus h was your horizontal shift. Your plus k was your vertical shift. Plus k was exactly what it should be. So if it was plus 5, you shifted up 5. The minus h, this is actually a shift to the right. And this can be rewritten. So we could rewrite this like y minus k equals f of x minus h. And your book will do that, and you'll see that in other places. And then this makes it a little bit more consistent. Okay, so this is minus k, but you have to think about shifting it to the other side. That gives you a plus k. So really your shift is opposite what you think it is. This isn't going down k units, it's going up k units. This is going right h units. And another way that we think of this is setting it equal to 0 and finding out what your x is, and that'll give you a positive or negative shift. Horizontal shift, I should say. Okay, so looking at this function, still the same exact parent function. Okay, and just as a reminder, I know that's on the other side, but our parent function was this. So what have we done? Well, notice now the k is not on this side. It's a positive 2 here. Okay, so, that commutative property where you can move things around with addition, that's happening here. Okay, this k can be moved anywhere. So this is going to be a shift up 2, because it's a positive 2. And then we've got x minus h. Which way are we going to be shifting this graph? Which way? Are we going to go left or are we going to go right? Well, it's x minus 4. And if you get confused, you can set that equal to 0, and you can say solve for x. So we're going to move right 4. So this is a shift right 4. So let's see if we agree. Let's see if that graph was given to us correctly. So again, I'll take a really easy point, maybe 0, 1. It should have been shifted up 2 units, 1, 2, and right 4. 1, 2, 3, 4. And it is. So I agree. Example 3 from your textbook. We're going to, again, they've probably written a lot more in your textbook, so you're going to want to read through that, but I'm going to go ahead and explain how I would do these problems. So the 3 graphs in this figure show 3 different transformations of the pre-image graph to the image graph y equals g of x. So that means that the pre-image graph, right, we've got the graph of g and we've got the graph of f. So the pre-image is the graph of f because the image graph is g of x. So that's after the transformation. Explain verbally what transformations were done and write an equation for g of x in terms of the function f. Okay, so the first graph here, I find that the easiest way to do this is to take my really obvious points and see what's changing. So I'm actually going to list out my points. So my original pre-image points, I've got -3, 1. I've got 1, 3. And I've got 4, -2. Now that's going to be the same. So f is the exact same graph. The pre-image graph is the same for each and every single one of these. And then I'm going to write down the point of the transformed graph, or of g. Okay, so this is f, and now I'm going to write down the points of g. So the first point I see was transformed. It's still -3, but now it's up 3. The second point still at 1, but now it's up to 9. And the last point, input still at 4, but now it's down to -6. So I notice that nothing is happening to the inputs. It's all happening to the outputs. So I ask myself, okay, is this a dilation or is this a translation? So I'm wondering to myself, well, if it's a dilation, then I can take all these outputs and I can multiply them by a common multiple to get these outputs, to get the image output. So let's see, 1 times 3 would give me 3. 3 times 3 would give me 9, and -2 times 3 would give me -6. So yeah, so really what's happening here is I have a vertical dilation by a factor of 3. Okay, and again, I knew that because nothing's happening to the x values, only something's happening to the y's. I started by looking for a common multiple, and if that hadn't worked, then maybe I'd ask myself, well, was it shifted up? But I think you could just look at the picture and realize, hey, every single point is not just being shifted up, right? Because I've got this point down here. So it's definitely a vertical stretch. Okay. All right, so now I need to write an equation for g of x. Oops, you can't see that. Write an equation for g of x in terms of the function f. So if I have a vertical dilation, back to here, a vertical dilation, we take that value of k and we multiply it by the function. Well, my value of k that it's been multiplied by is 3, so it's really just 3 times f of x. So g of x is going to equal 3 times f of x. Okay, moving on to the next one. So I'm going to do the same thing. I'm going to write down my 3 original points. So -3, 1, 1, 3, and 4, -2. And then I'm going to write down my transformed points. So -3, -1 becomes -3, 7. 1, 3 becomes 1, 9. And 4, -2, let's see here, is still 4 for the input, but it's up to 4 for the output. So again, I look at this and I'm asking myself, okay, did anything change in the x's? Nothing changed in the x's, only the y's changed. Okay, so then is there a multiple that I can multiply each of these by to get this number? So 1 times 7 would give me 7. Well, 3 times 7 would give me 21. So that's not working, okay? And I should be able to look at this too and say to myself, it doesn't look like my pre-image got stretched at all. So I'm going to say this is probably a shift. Now let's see. If I add or subtract something to all of the original outputs, do I get the new outputs? Well, 1 plus 6 would give me 7. 3 plus 6 would give me 9. And negative 2 plus 6 will give me 4. So yeah, as a matter of fact, this is a vertical shift of 6. Or I could say vertical, maybe I should use better vocabulary. How about a vertical translation of 6? So basically what my original function was, I'm just going to add 6 to it. That should be really simple. So this is like that plus k. So hopefully that's pretty straightforward for you. I'm just going to put some dividing lines here. Okay, and then the last one, I'm going to do the exact same thing. So I'm going to start with my original points. It's the same pre-image, so same original points. All right, so my first point, negative 3, 1, turned into negative 6, negative 6. My second point, 1, 3, turned into 2, negative 4. And my third point, which was originally 4, negative 2, turned into 8, negative 9. Okay, so first of all, the x's changed. So let's try and figure out what happened with those x's. Now, you should be saying to yourself, well, I can see for a fact that this pre-image got stretched, and it looks like a horizontal stretch to me. I'm also thinking, it doesn't look like it got vertically stretched, but it does look like it got vertically moved down. So let's see, are the y's different? The y's are also different. Okay, so starting with those x's. So in your notes, anytime that you're going to have that horizontal dilation, you're going to take your x coordinates, whatever was originally your xy becomes x divided by k. So you have to ask yourself, what did you divide your all your inputs by to get your current inputs, your inputs of your new image? Okay, so for example, I have negative 3. What did I divide that by to get negative 6? So what is this question mark? So negative 3 divided by what would give you negative 6? Hopefully you're saying to yourself, question mark should be 1/2. Right? Negative 3 divided by 1/2 will give you negative 6. Now let's make sure that that works for the rest of them. If I take 1 and divide it by 1/2, do I get 2? I do. If I take 4 and divide it by 1/2, do I get 8? I do. Okay, so I know that I have a horizontal dilation by a factor of 2, right? So it was stretched by a factor of 2, which means that my k that I'm multiplying my input by is 1/2. So I'm going to go back to my notes here. What I'm talking about is this k that I'm multiplying my input by is 1/2. Okay, so k is 1/2. So really I know that this is going to be my k, okay? All right, so I know then so far, let me go a little further down here because I've got more that I need to do. Let's go up here. So I know that I have a horizontal dilation by a factor of 2. Okay, so I know that. And then I also know that, let's look at our y's. So I went from 1 to negative 6. I went from 3 to negative 4 and negative 2 to negative 9. So can I multiply everything by something? I think we already said we know we don't have a vertical dilation, but let's just double check. If I wanted to go from 1 to negative 6, I'd need to multiply by negative 6. Well, that's not going to work on the rest of these to give me these outputs. Okay, let's see if there's then a shift or a translation that happened. So to go from 1 to -6, I had to subtract 7. 3 to -4, well, that's also subtracting 7 from 3. And -2 to -9, that's also subtracting 7. So I know that I had a shift down, or I had a vertical translation of -7. Okay, so my overall new image, g of x, I took f of x. Now inside, I have that k that's going to be multiplied by x. And then I subtracted 7 from that. And if you wanted to put plus 7 over here with g of x, you could do that too. So I found this nifty little table online, so I figured I'd just go ahead and give it to you guys. A lot of this you guys already know. So anytime that you have a negative, so you're multiplying your function by some negative, you're going to reflect it over the x-axis. Now, if you end up negating your input, you're going to reflect it over the y-axis. If you add something to your entire function, you shift it up k units. If you subtract something from the entire function, you shift it down k units. That x plus k means that you shift left. I know it's opposite. And the x minus k means that you shift it right. And probably the new stuff, it's not too new, we definitely explored this last year, but you're going to get better at it this year, is that anytime you are multiplying by k, you're going to this is k times the entire function. So the entire function represents the output. So you multiply the y values or the output by k. And then anytime that you're multiplying the input by something, now you need to divide the x values by k in order to get your new x values. And so those two things go along with these two pieces of information here. So this was important. I found this. I thought it was a great little cheat. I don't know if it's cheating, but a little guide for you guys to remember, and maybe even write that on your index card when you do take a test. I just want to add one more here. So I'd like us to look in our textbook. There's an exploration I'm going to have you guys do in class tomorrow, if we have time. And this is on page 20. And it's number 5. So this is one that we haven't gone over yet. But your pre-image is your dotted or the F graph. And then your image is the G. So notice what's happened to all the outputs. Originally, some of the outputs were negative, and now they all became positive. So what makes things that are negative positive and keeps things that are positive positive? Hopefully you're thinking to yourself, absolute value. You are correct. So basically what I need you to remember is that if you take the absolute value of a function, you will reflect across, I don't know how to spell, x-axis any negative outputs. So anytime you see a graph that used to have some negative outputs, and then the image, so the pre-image had some negative outputs, and then the image doesn't have any negative outputs, there's usually an absolute value involved there. All right, moving on, I'm going to do a couple problems from your homework. I'm going to do a couple of the evens. So page 21, looking at number 6, and I copied it all right here for you. Okay, so we are given f of x equals 9 minus x squared. Okay, and we're going to write the equation for g of x in terms of x. Oh, actually the equation, sorry. The equation is this. This was the equation. that we're given. So this is number 6 in your book, and I copied all the directions. Okay, so we're going to write the equation for g of x in terms of just x. Okay, so notice that this is in terms of f of x. Okay, so we're going to come up here. I'm going to do it right next to it, okay? So I noticed that I multiplied the entire graph by 1/2, right? I'm multiplying the entire function by 1/2. Okay, and then I'm taking my x and I'm adding 3 to it. So my new function becomes g of x equals, well, that function gets multiplied by 1/2, and the function is 9 minus x squared. Well, x is no longer by itself anymore. We added 3 to x. So we're going to do the quantity x plus 3 squared. Okay, now the second part is we're going to plot the graphs. So we're going to plot both f and g. Okay, so one of them will go in y1, the other one will go in y2. So do it on your calculator for practice. Don't just sit there and watch me do it. Oh, cool. So I'm going to do 9 minus x squared. And then the other one's going to be 1/2 or 0.5. That'll also work. And then I'm going to do 9 minus, and then in parentheses, x plus 3 squared. Oops, that didn't work out very well. Let's delete that. There we go. Okay, I'm going to make sure that my window is set from -10 to +10, just like it's telling me to do. So use a window from -10 to +10, and that's a standard window. So if I actually click on zoom and I choose Z standard, now if you have colors on your graphing calculator, this becomes really easy to realize which one's the original function or the pre-image and which one's the image. It might be easier for us without color to look at the table. Either way, you should be able to plug in numbers and get out values. So I could, for example, in my original function, plug in 0 and know that my output is 3. So the one that is centered is actually my pre-image. And then this one I can see had a shift left of 3, right? So this right here tells me to shift left. And this tells me that I'm going to have a vertical shrink. All my outputs are all going to be half of what they used to be. Okay, so that should help me in graphing this. You can also go to the table, because sometimes it won't be so easy to figure out which one's the pre-image and which one's the image. And so it's also really nice to use the table. Actually, I'll go ahead and I'll use the table now that I have a visual representation. I'll use the table just so that I can get exact numbers. Or you can do inputs and outputs. I'm not going to use the negative y-axis because it doesn't look like I need it. And it looks like the highest I go up to is 3, so this is kind of easy. And I go over 1, 2, 3, 4, 5. It looks like -6. I actually didn't even need the positive. Oh yeah, I do need the positive x-axis. So I'll go ahead and I'll use my table just to get some exact numbers here. So it looks like at -3, my y1, I'm going to have 0. And my y2, which was the transformed, my output's going to be 1.5. Okay, and I'm just going to use the whole numbers here. So at 0, my pre-image had an output of 3. And my image has an output of 0. At positive 3, my pre-image had an output of 0. So this is my initial function, or my pre-image. Looks something like that. Not as good as the actual graph. And so this is going to be my f of x. And I'm not done getting the rest of my outputs, so I think that I need to go on the negative side. And at negative 6, at negative 6, I see that my transformed function, or my image, has an output of 0. And so this here is g of x. Okay, so that's B. So let's see, let me label this. So this was A, this is B, and now we're going to do C. So describe how f of x was transformed to get g of x, including whether the transformation was inside or outside. Okay, so first of all, I had a y dilation, or I had a vertical shrink. Okay, I'm going to call it I'm going to do both. So I'm going to say y dilation. I already said vertical shrink up here, by 1/2. And so that's not happening to the input, that's happening to the output, right? It's happening to the function itself. It's not happening to the input directly. So that we call an outside transformation. I'm just going to abbreviate. The other thing that I had now, this plus 3, shifted everything left. We'll call that an x translation. And if I'm going left, I'm going negative, in the negative direction. And again, that's happening to the input, right? So that's happening to the input here. So that's an inside transformation. Okay, we're going to do one more example together. Last one. This is page 22, number 20. We're going to sketch the graph of the image function g on a copy. So you'll have this, you don't have to write in your textbook. I'll actually give you like a handout. So when you're doing the odds, you'll have a handout where you sketch these. Okay, and then identify the transformations that are done. Okay. So first of all, maybe I'm going to do that backwards. So I know that this plus 4 is going to be a vertical shift up. And now I've got this 1/2 being multiplied to my input. Okay, so that's going to be right here, right? That inside k happening to my input tells me that I'm going to divide my x values by k. So I'm going to divide all my x values by 1/2. Now dividing something by 1/2 is really the same thing as multiplying by 2. So that tells me that I've got a horizontal dilation by a factor of 2. Okay, so I'm going to do all of those things to my function now. Okay, so I'm going to take each original point, and then I'm going to transform that point, and I'm going to do that over here on the side. So my original points are -4, 0. That's a pretty easy one to see. I think I got -2, -2. I've got 0, 0, 2, 2, and then 4, 0. So each one of those I'm going to do a vertical shift up by 4. So that just has to do with the y values, right? Vertical shift up by 4, add 4 to your y. So I'll do that for each one. We'll do that part first because that's the easiest part. Okay, then I've got this horizontal dilation by a factor of 2. Or in other words, my k is 1/2. So I'm going to take each of these and divide it by 1/2, which is the same as multiplying by 2. So I'll get -8, -4, 0, 4, and 8. Okay, so I'm just going to plot my new points on there. Okay, and it should have a similar shape, but it should be stretched and shifted up.